So this week we are going to take a look at chapter 5. So this is our last real chapter where we're going to be studying a new type of function in the pre-cal part of this class. So we've done lots of different kinds of functions. We've done radicals, like with roots. We've done rationals. We did quadratics. They look like U-shapes and parabolas. So this will be the last one we look at. All right, so first thing I want to do is just compare these two things, not even drawing them yet. I'll draw them in a little bit. But just looking at how they compare to each other. When you write something with a number lower and then something higher, okay, there's a name for each of those pieces. Does anybody remember what you call the thing that's written up a little bit higher?
Exponent.
Yep, that's the exponent. And how about the thing that's below that?
Base.
That's called the base. And in each one of those, they have a base and they have an exponent. The difference is one of them is a polynomial and one of them is what we call exponential. The one on the left, x to the second power, that is a polynomial. And we've studied that kind of graph before. Specifically, that's a quadratic. Okay? And if you graph it, it would look like a U shape. Does anybody remember the name of that? It looks like a U shape, but it has another name. Parabola. Yep. So the one on the left would look like a parabola. Something like that. Okay. Does everybody have that top part? In each case, we have a base and an exponent. Okay. So what makes something an exponential versus a polynomial is the type of base and the type of exponent. When the variable is in the base, okay, like the one on the left, x squared, okay, or something like 2x cubed. Those are both examples where the variable is in the base and the exponent is a non-negative integer. Okay. That makes something a polynomial. So you couldn't have like 3.4. Okay, you can't have decimals, and you also can't have negatives. Okay. So if the exponent is a number that's not negative and it doesn't have any decimals, that's okay with a polynomial. Now, if you look at the one on the right, 2 to the x, what do you notice about the exponent in that one? How is it different than the one on the left? Anyone see a difference between the exponent for the one on the right and the one on the left? Yeah?
The variable is the exponent.
The variable is the exponent. That's the big difference, yeah. So when the variable is the exponent and it's not in the base, and then the base is the number, that makes something exponential. Okay, so this is what we're going to look at today. When the variable is the exponent and the base is the number. Now, the number can be a lot of different things in the base, but there are a couple of restrictions. First of all, the number does have to be positive, and it can't be a 1. Okay? But anything other than 1, as long as it's positive, it's okay. So 2 to the x, 4 to the x, 5.7 to the x. Yep, decimal's fine in the base. It just says the base has to be a real number. Remember, real numbers include decimals. Okay? But it can't be a 1. That's the only one it can't be. All right. So any question on the difference between polynomial and exponential? Yeah?
Why can't it be a 1?
Because if it was a 1, and let's make a table of some of the answers here. If x is 2, what's 1 to the second power?
1.
1. How about if x is 3? What's 1 to the third power? 1. Let's see if x is 5. What's 1 to the fifth power? 1. So the problem is, since you're getting the same value all the time, that's called a constant function. Yeah. As long if that's not a 1, then the answer you get will change. And that's what has to happen with an exponential. It has to change. Yeah. Good question. And we're not even going to talk about what happens with negative numbers. It's just you definitely can't do that. It's a little more complicated. Why? All right, let's look at what an exponential looks like. Okay, so I'm going to do 2 raised to the x, and I'm going to do zoom 6. And what I'd like to look at there is the domain and the range. Okay, how far left and right it goes, and up and down it goes. Well, first thing you'll notice, exponentials, they curve up very fast, right? That's a characteristic of an exponential. It starts to curve up very fast. Specifically, if it's curving up, we call it exponential growth. If it's curving down very fast, there's another name for that. Okay, but it's not called growth. I'll show you what it's called in a little bit. All right, so let's start with the domain. How far left and right does it look like that graph in blue is going to go?
Infinite.
Yeah, it's going to go left and right forever. This part here just kind of keeps curving up, but it also keeps heading to the right slowly, right? But it does go to the right. So your domain is all real numbers, and that's every exponential. Because we will talk about shifting these and stretching them, moving them left and right. But no matter what you do, you cannot change the domain. The domain of an exponential function is always all real numbers. Right. Now let's look at the range. Does it look like that graph in blue goes up forever and down forever? What's that?
Up forever?
Yeah, it does go up forever. Okay, so the range will go to infinity. Does it go down forever?
No.
No. It starts to, looks like it starts to level off. What number does it look like it's leveling off at as it comes down?
0.
0. And we actually have one of these in there. Does anybody remember when you draw a dotted line and something gets close to it but never reaches it? What you call that?
Asymptote.
An asymptote. Yep. And if I go into the table and I type in like -10, okay, so that's way on the left side of my graph, I'm just barely above the y-axis. That's 0.000976. So very, very small. All right. If I keep going further to the left, like -200, now I'm at like 0.061 times and then a 6. It's a very small number. Okay? So it gets close to 0, and eventually it might even say 0, like if you put in a big enough number. But remember, it's never really 0. Okay? It gets close to it, but it never reaches it. It's just the calculator ran out of decimals. So that's all. Okay. Actually, let me write that down. So the range is from, we said, getting close to 0, but not including it, up to infinity. For this one, I'm going to put never changes. Okay, no matter what you do, that one never changes. This one can change. Okay. How could it change? Well, let's say I do something like this. If I put a +1 on the end of it, what number does it look like as you go to the left that it's curving down and getting closer to now? It's getting closer to 1 now. So the range in that one is 1 to infinity. Yeah. So you can modify the range depending on what you do. And again, remember when you are talking about exponential functions, this is just a reminder, I already said this before, that the base is a positive number and it cannot be 1. And I already talked about why it can't be 1. Okay, so just a reminder of what's on the other page. So these are all examples of exponential functions. So the two things you want to look for: do you have a base that's positive and not 1? And do you have a letter in the exponent? All of those meet that criteria. So those would all be exponential. These are not exponential. Okay. This one has a base that's a variable. No, can't have that. This one, again, you're supposed to have an exponent that's a letter. There's no exponents that are letters there. And that last one, well, that's kind of a combination of two things. It's rational, because it's a fraction, and it has a root in it. So it's kind of a mixture of rational and radical. But it's not exponential. So is there any question why the top 3 are exponential and the bottom 3 are not? Specifically, the top 3 are not only exponential, they are exponential growth. And if you don't know what makes them growth, you will shortly. Okay, so let's look at the difference between those two graphs. 2 to the x and 3 to the x. All right, so I already have, I modified it. So let me put 2 to the x back. Just get rid of that plus 1. And 3 to the x. Okay, so 2 to the x is in blue, 3 to the x is in red. And what do you notice about the red one compared to the blue one?
Goes up faster.
Yeah, it goes up faster, right? The curve is a little bit sharper. And if I did 4 to the x or 5 to the x, that one would even curve up a little bit faster. Okay, the key is it starts to curve up right there. That's where it starts curving up once you get past the y-axis. All right, so that one's not too hard to compare the two because we can just draw it, we can look at it. And both of those numbers were positive. Okay, that's a good thing. And both of these letters were positive. Right? If you have a problem where one of the letters is a negative, that's going to be a little bit of annoying. Okay, to compare these two, we don't want to have this negative here. Okay, so I'm going to show you how you can write something that's exactly the same, but it doesn't have a negative. Because that negative is going to mess us up. So this is what's going to help us to analyze graphs when there is a negative in the exponent. We're basically just going to get rid of it by doing this. Okay. If you raise something to the -1 power, does anybody remember what that means? Like if I had this, and I wanted to write that without a negative number. Yep.
You would be 0.2. Like if we distributed exponents.
It is going to be a decimal, but it's not won't be 0.2, but it is definitely going to be a decimal. Yeah.
Would it be a root?
Nope, it won't be a root.
You turn it into like the fractional exponent, right?
We turn it into a fraction, but there won't be any more exponent when we're done. Anybody remember what 2 to the -1 turns into?
1/2.
It turns into 1/2. Yeah. How about 2 to the -3? Does anybody remember what fraction that would turn into?
3/2.
Not 3/2.
2/3.
So let's type it in and just see what happens. 2 raised to the -3. It gives us 0.125. Does anybody know what fraction that is?
An eighth.
That's an eighth. Yep. Okay, let's try one more. How about 2 to the negative 4? Anyone have an idea what's going to happen to that one? What is it?
1.5.
No, 2 to the negative 1 is 1/2.
So would it be 1/16?
Maybe 1/16. Right, how about 3 to the negative 2?
Quarter. That's going to be 1/9.
That would be 1/9. Yep. People seeing a pattern here?
Yes.
How about, let's just do one more. How about 4 to the negative 2? What would that one be?
I think same as 1/2.
1/16. Yep. So what's happening there? What's the pattern? Okay, so like you are making it into a fraction, yeah. Yep.
So it's like the negative and the exponent, kind of like you just disregard that, and then you do 2 to the exponent, you put that in the denominator, and then you put a 1 with it.
Yeah, so it's like it causes it to flip, exactly. So what do you think this one would be? If you raise a to the negative 1 power,
1/a.
it would be 1 over a. So instead of writing, so like if it's 4 to the second power, you just write 16. Well, if it's 4 to the negative second power, you write 1 over 16. So the negative in an exponent causes something to flip. Okay. And that is what's going to help us here. So I'm just going to move that over a little bit. If you have something that has a negative in front of the exponent, just like we're going to have right there. This is going to be exactly the same thing. To get rid of that negative in the exponent, you take this, don't erase it. Take that and flip it. And then by flipping it, that gets rid of the negative exponent. Because that's what a negative exponent means. It means to flip. So if you had something like, let's say, 3 to the negative x, what do you think that would be if I rewrite it without that negative exponent?
1/3.
Yep, 1/3 to the
X
x. Yep. You just take that number that's right there and you flip it and then get rid of the negative. And the reason that's important is because when you look at a problem like this, if I said to you, what's the base? A lot of people would probably say 3. But the base is really 1/3. Okay? And that's because it has this negative exponent and that messes things up. So we don't want a negative exponent there. And you'll see what happens when the base is less than 1. That's important. That causes something to happen in the graph. So I told you there's one type of exponential called growth. Well, there's another one called something else. All right, so now let's graph these two. F of x is fine, okay, 2 to the x. G of x is not fine because it has a negative in the exponent. So what can I make this to get rid of that negative?
1/2.
Make it a 1/2. So what I'm really trying to show you here is what is the difference between graphing an exponential with a base bigger than 1 and a base smaller than 1. What's going to happen? Okay, well, 2 to the x, we already know what that looks like. We got that one right there. What do you think is going to happen when I do 0.5 or 1/2? You can do it either way, to the x. Yep.
That's going to be decay instead.
Right. This is going to be what we call an exponential decay graph. So it's going to look like it's a mirror image of the blue one. It's going to, as you go to the right, it comes down. And it is a mirror image. So the blue one is called exponential growth, and the red one is called exponential decay. Let me keep both of those up. Just put that right there. And I want to look at the domain and the range of each of them. Okay, so just to color code it, f of x is the blue one, g of x is the red one. Okay, so let's look at the domain. What's the domain of the blue one? I think we already talked about that one. How far left and right does the blue one go?
Negative infinity and infinity.
Mhm. Negative infinity to infinity. And how far left and right does the red one go?
Negative infinity and infinity.
Right. Every exponential function always has a domain of negative infinity to infinity, and that never changes. Doesn't matter if it's growth or decay. Never changes. All right, now let's look at the range. Start with the blue one. How low and how high does the blue one go? Low, and we want to go low to high.
0.
0 is the low. And what's the high? Infinity. Yep, the blue one just keeps going up forever. And now let's look at the red one. How low does the red one go? And then how high does it go?
Zero and infinity is one.
It's the same thing. Yeah, it doesn't go any lower than the blue one. It goes as low as 0, and it goes up forever. Yep. So even though they are mirror images of each other, they have the same range. Yep. Now, if I mirror imaged it this way, that would be different. That would have a different range. Okay. But I didn't flip it up to down. I flipped it left to right. So now, let's keep that up. And instead of just thinking about it with like a 2 and a 1/2, I want to generalize it to basically anything. Right? It doesn't matter if this is a 3 and a 1/3, a 5 and a 1/5, a 9 and a 1/9. It's going to look pretty much the same. So now let A be any positive real number you want. 2, 3, 4, 7, 12, it doesn't matter. F of x is going to look something like the blue one. Again, the one on the left is specifically 2 to the x, but 3 to the x is going to look pretty much the same. It's just going to curve up a little sharper, but it's still going to have the same look. And g of x, in general, is going to be some kind of graph that curves down. Depending on A, it might curve down a little sharper, but still going to look something kind of like what's on the left. All right. So now let's start with the blue one. That top line is saying as x approaches infinity. If you're approaching infinity, which way are you heading? To the right. So this is saying as you head to the right, what happens to the y value? So look at the blue one. As you keep following the blue one to the right, what's happening to the y value?
It's going up.
It's going up, and what is it approaching?
Infinity.
Yep. So in other words, every exponential growth function, as you head to the right, goes up. All of them. They might go up a little sharper or a little slower, but they go up. All right. Now, below it, as x approaches negative infinity, which way is negative infinity? To the left. So now, looking at the blue one, as you head to the left, what are you getting close to? You're getting close to, but are you ever reaching it?
No.
No. You're getting close to it, but you're never reaching it. Now, is it always 0? No, but it is always a number. Okay. I think I showed you guys an example where I did a +1, and then it shifted it up 1. Okay. But it's always a number. All right. Now, let's look at the red one. On the red one, as you go to the right, what are you getting closer to in this graph? You're getting closer to 0. Again, is it always 0? No, but the idea is you're always getting closer to a number, okay? In a graph that looks like the red one. Again, that's called decay. How about in that decay graph, as you head to the left, what happens to your y value there?
Negative infinity.
Well, as you approach negative infinity, what's happening to the y value? It's not going to negative infinity. That would mean it does that.
It goes to infinity.
It's going up, yeah. So as you head to the left, the y value goes up to infinity, not negative infinity. Okay, so the top one, this is what we call growth, and the bottom one is decay. And that's pretty standard for how they look. One side goes to infinity, and the other side goes to a number. Which side goes to what? Well, it depends if it's growth or decay. And what do you think the difference is looking at this number? What do you think makes this one growth and that one decay? There's a number that if you're above it, you'll be growth, and if you're below it, you'll be decay. Anybody have an idea what? 1. Yeah. 1 is the key difference between whether your graph is going to be what we call growth or decay. If the base is greater than 1, that's growth. Growth looks something like that. Okay, curves up to the right. If you have something between 0 and 1, like 1/2, 1/3, 0.6, that's going to be decay. And decay looks something like that. The sharpness of the curve, that's controlled by how big or small the base is. Okay, so any question on that? All right, so that's kind of just a little bit of a background about what about exponentials. Now we're going to look at how we can transform them. I already showed you guys an example right here when I put a +1 on the end. Does anybody remember what that +1 did to it? Which way it shifted it?
Up.
Yep, it shifted it up. So when you add a number on the end, it shifts it up or down. We'll go through all of them. But the nice thing about them is they are exactly the same as the transformations that we've already done. Okay, but I'll make the chart and I'll do the A, B, C, D, just so you can see it again. Okay, so let's see, like y equals, let's do, I'm just going to say here you have some base. I don't know what the base is going to be. It doesn't matter. Okay. In a minute, I'm going to do a problem where the base is a 3. Whatever the base is. And I'm going to label what each one of those do. Okay, I use the letters A, B, C, D because when they ask you to list the transformations needed, you have to put them in a certain order. And it's A, B, C, and then D. You just have to identify what each one of them are. All right, well, we just did D, so I guess we could start with that one. D was adding or subtracting a number on the end. In which way did that move it?
Up and down.
Up and down. So up and down is called a vertical shift. Positive is up. Negative is down. So that's D. Let's do A. A is adding and subtracting, okay, like D. But now it's inside the exponent rather than outside the exponent. So it's going to have something in common with D, but then it's going to have something that's different. Anyone have a guess what the A is going to do? Yep.
Horizontal.
Yep. Any adding or subtracting is always a shift. When you're inside, that's horizontal. Outside is vertical. So that is a horizontal shift, and this one is backwards. Horizontal has always been backwards, just the way it works. So which way would positive move it?
What?
Positive would move left. Yep. And negative would be to the right. All right, let's look at B. Now, B is still inside the exponent, so it's going to have something in common with A, but it's multiplication. So anyone have an idea what B is going to do?
Horizontal stretch.
That's horizontal stretch, yep. So horizontal stretch. And it is backwards. Okay, so if you had a number like, I'll just do an example, just do a little example here to show you something. If you had 2 to the 3x, that is a horizontal stretch by 1/3. And again, you might say, well, why? It's a 3. Well, it's backwards, right? When you put a 3, the bigger you make the number in front of x, the smaller the graph gets, the more compressed. If you had something like 4 to the 1/2 x, you think, oh, 1/2, that's a small number. No, it doesn't make it smaller, it makes it bigger. So that's a horizontal stretch by 2. I just didn't have enough room to write that up. Okay. Luckily, A and B are the only ones that are backwards. Okay, how about C?
Vertical stretch.
Right, now we're outside. We are outside the exponent, so now it's the vertical stuff. Vertical stretch. And that is not backwards. So if you want an example of that, 4 times 2 to the x, that's a vertical stretch by factor of 4. And no, you can't do 4 times 2 and write 8. You can't, because there's an exponent there. Pem dash, you gotta do exponents first. So, vertical stretch by 4. And then if you had something like 1/3 times 2 to the x, that's a vertical stretch by 1/3. So a couple examples if you need to look back at that. Okay, and the last thing that can happen is the B or the C could be a negative. And we actually already looked at what happens when the B was a negative. That was the graphs that we looked at. I don't know if I still have them. Yeah, that's actually the graphs right here. If B is a negative number, what does that cause your graph to do? Flip over which axis? The y-axis. The blue and the red one. Just erase the one that I drew in. The blue and the red one there, those are reflected over the y-axis. Yep. So let's add that in. So for B, I'm just going to say if negative, reflect over y-axis. You could also say horizontal reflection, means the same thing. And what about, where did I put C? C. If negative, reflect over, what do you think would happen if C is negative?
X-axis.
X-axis. Yep. So a reflection over the x-axis would look like this. It would be like the top one versus the bottom one. That gives you a total of 6 transformations. A, horizontal shift. B, horizontal stretch. B, reflection over the y-axis. C, vertical stretch. C, reflect over the x-axis. D, vertical shift. So A and D do 1 each. B and C can do up to 2 if they have the negative in there. Okay, so any questions on that chart? Okay, let's try it. Not every transformation problem is going to have all 6. This one only has, well, I'll ask you how many it has. The other thing, when you are doing transformations, you will always be comparing two things with the same base. So you're comparing 3 to 3. You would never compare something with a base of 3 to something with a base of like 5. It doesn't work. So you got to compare things with the same base. All right. So now, first of all, to change f of x, we'll call that the original, into g of x, how many steps or how many transformations is it going to take? Yeah?
3.
Yep, it's going to take 3 transformations. So start with A, and then go B, C, and D. Anything that you don't have, we just skip it. Okay, so let's start with A. Do we have a number in the spot for A? Yeah, what number is it, Ricky?
1.
Yep, plus 1. What's that plus 1 going to do?
The left.
Plus 1, yeah, plus 1 is going to move it left 1. So let's just say shift left 1. Perfect. Okay. We got A. Now we go to B. Do we have a number in the B spot? You think, Dylan?
No, I don't think so.
No. I mean, we do. We have a 1 there.
Yeah.
But the 1, that doesn't do anything. It has to be something besides a 1. So, nope, we don't have to worry about B. So we're going to skip B and we're going to go to C. Do we have a number in the spot for C?
Yeah.
Yeah, what number is in that spot?
2.
2? So how do we describe what the 2 is going to do?
Stretch.
Yep,
By that.
exactly. Vertical stretch by factor of 2. That means it takes the graph and it makes everything twice as tall. All right, so we did the C. Now we go to D. Do we have a number in the spot for D?
Yeah.
Yep. What number is there?
Negative.
-5. So that's going to move my graph which way?
Vertical shift down.
Yep. Shift down 5. If you say vertical shift down 5, it's the same thing. As long as you tell me a direction and you tell me how much. Down 5. Shift down 5. That's it. Those are transformations. Okay, so it didn't have all 6, but it had 3 out of 6. Any question on that one? We're not. We're going to talk more about that tomorrow. Okay. So the last thing we're going to look at is a couple formulas. So we've already kind of been throwing a couple words around: exponential growth, exponential decay. We're going to look at 2 examples of that in a word problem. When you have a population that's increasing at a percent, like let's say the population of the town is going up 2% every year, that's exponential. That means over time, the amount of people, it's going to start to curve up very quickly. And in a lot of things, exponential growth can be, especially with like when you're dealing with like life or like bacteria, it can be something that can get out of control pretty quick. It's like if you had a bacteria that was growing exponentially, if it's a harmful kind of thing that's not good for people, that's bad, because that means it's going to grow extremely quickly or spread very quickly. So here's the formula that we need to figure out exponential growth. Okay, it's got 3 letters in it. The first one is P P, which is an initial amount. So it could be an initial amount of people, could be an initial amount of bacteria, an initial amount of money, if you were dealing with like a banking account. Again, we don't get into the banking stuff. That's the 2 sections we skip. They're still really good sections. It's just, it doesn't really fit with the class that you guys are in. So P is an initial amount. R is a rate. What's important about that is it has to be changed to a decimal. So the percent always needs to change to a decimal. So if you had something like 12%, what's 12% if you write it as a decimal? 0.12. Yeah. 3%, 0.03. So you've got to change your percent to a decimal. And T, well, I didn't label that. That's time. So for example, you might say that the population of the town is going up 2% each year. Tell me how many people are going to be in the town in 25 years. So it's how much time has gone by. Now, that's exponential growth. There's only one thing that changes in that whole formula, and it turns it into exponential decay. Anybody have a guess what would change there? The rate? Yeah, instead of 1 plus r, what do you think it would be? It becomes 1 minus r. Yep. So exponential decay in like a real life problem, that can also be an issue. Like let's say you had forest, and the amount of forest was decreasing exponentially because they were cutting all the trees down. Well, that's not good either. Another type of exponential decay you might know of, if, I don't know what science class you've taken so far, but if you've ever talked about like half-life, that usually applies to like nuclear or radioactive material. That's a specific type of exponential decay. It's a 50% decay, half-life. So we'll look at an example to finish up with that. Okay. Any question, or does anyone need to copy down the growth or the decay formula? Okay, so let's look at this problem. It says a town has a population, we'll think of that as the starting value, and the population of the town is going up 2.5% per year. What makes that exponential growth? Yeah? Increasing by what? A percentage, yeah. If I said to you, the population of the town is going up 100 people every year, that's not exponential. If you just add 100 every year, that's a linear growth. It's growth, but it's linear. It's not exponential. So the first thing it says is to model this with a function, and then use a graph to find when the population hits 100,000. Okay. Another way I could ask that is use a graph to find when the population doubles. 100,000 is double 50,000. Okay, but we got to start with the equation. So we're going to write down a formula that represents the population of a town as a function of how many years have gone by. So I'm going to use P of t. And you could call it f of x. I just think P makes more sense because you're talking about population. So P of t. Okay. What's the very first thing that comes after the equal sign in an exponential growth formula? What do we call the thing that we write down? Yeah?
What is it? Population now?
Yeah, right, the starting value, the initial amount. What's the initial amount of people in this town?
50,000.
Yeah, or at least when we started measuring, it was 50,000. Okay. You don't have to give me any specific numbers for R, but what would you put inside next to it? You always put 1 plus R. Okay, now we need a specific number. What's R in this case? Yeah?
0.025.
Right, don't put 2.5. If you do that, that's 250%. It's 0.025. And t, well, that we don't know. That's what the question is going to be about. How many years have to go by for the population to hit 100,000? So I'll simplify it as much as we can. 1 plus 0.025. That's all you can do. You cannot multiply 50,000 times 1.025. You have to leave it just like that. There we go. So that's the first part, to create a formula for our problem. Any question on the formula? Okay, now part 2, it says use the graph. So let's make a graph of that. So let's put in 50,000, and then in parentheses 1.025. Now when you type it in, you do have to use x as the variable because that's how the calculator works. Now I could start with zoom 6, but zoom 6 is going to give me a window from -10 to 10 and -10 to 10. What's the problem with that?
Nowhere close to.
Yeah, where does our population start?
50,000.
50,000. So I'd say we should set our population to start at 50. And then how high do we want to go? Well, that's going to come in part 2. We want to see when the population hits how much. Okay, so I would let's just go a little extra. Let's go 125,000. Now, x is representing how many years have gone by. What kind of numbers definitely don't make sense for the amount of time? Yeah, you can't use negatives. We can't say what will the population be in -5 years. We could look that up in a book. It's already happened. So smallest amount of time that could go by is 0 years. And the most amount of time, well, there's no limit. We can have as many years go by as we want. So let's go up to 40 years. If we don't hit 125,000 people within 40 years, we'll go a little more. So there's our population. It's not a like steep curve, but hopefully you can tell it's not straight. It is curving, but it's slow. All right. So now we've got our graph. So that's good. When does the population hit 100,000? Well, there's 2 places we could plug that in. We can either fill in 100,000 here, or we could fill it in there. What is the 100,000? It's population. Which one of those red boxes is population? T or P of T? P of T. So that's going to go right there. So we're going to fill in 100,000 right there, and now we're going to solve it. But we're going to use the graph. And the reason we're going to use the graph is because in this class, we haven't talked about how to solve an equation like that with algebra. What do you think makes this equation a little bit hard to solve with algebra? And it's definitely not something you see in Algebra 1. The exponent. The exponent is a variable. That's an exponential equation. In the next section, we'll learn how to solve it with algebra. Okay. So what do you think I'm going to do on my y equals screen to represent what's in that black box? Yeah.
Make a second line.
Mhm. Make a second line at 100,000. Okay. So now we've got the growth of the population in blue. We've got a mark at 100,000. And what do you think we want to find now? Where they intersect. Yep. So second calc intersect. Let's put that there. Let's move it down. So the question is, when the population hits 100,000. Okay, so how long is it going to take for the population to hit 100,000? Yeah, 28.07 years. So 28.07 years, the population will be 100,000. So you just got to make sure you zoom out enough to see what you're trying to see. Any question on that one? So as I kind of mentioned this in the last problem, be careful about including negatives because sometimes it doesn't make sense, okay, especially when you're dealing with time. Now, let's look at another example of exponential growth. This is much more rapid than the last problem. This is something that's doubling. Okay, doubling. Say we had 100 bacteria, and it doubles every hour. Time 0 means the beginning. It's before any time has passed. So how much bacteria do we have at the very beginning of this experiment? 100. How much bacteria do we have after 1 hour has gone by?
200.
200. Now, instead of thinking of it as 200, think of it as the initial amount times 2 to the first, because that's going to help us to see a pattern. How much bacteria do we have after 2 hours? 400, or the initial amount times 2 to the second. Now, we are going to have 800 after another hour, but what do you think? How would you write 800 using that pattern I'm trying to show you? 100 times 2 to the third. Okay, initial amount times 2 to the number of hours that have gone by. That's the pattern. Okay, how about after t hours? What do you think the formula is going to be?
100 times 2 to the t.
Yep, 100 times 2 to the t. So in general, the formula for something doubling is the initial amount times 2 for doubling, and the exponent is t divided by the length of time to double. Now, the reason it has to be t divided by the length of time to double is because this is the number of doubling cycles, which in this case is equal to the amount of hours that have gone by. If 1 hour has gone by, it's doubled once. 2 hours, twice. 3 hours, it's doubled 3 times. But let's say I had something that doubled every 5 hours. If something's doubling every 5 hours, and 5 hours have gone by, how many times has it doubled?
Once.
Just once. Okay? If 15 hours have gone by, how many times has it doubled? 3 times. Right? So this, what's in that red box, has to be the number of times it's doubled. And to figure that out, you take how much time has gone by, like 15 hours, and divide by how long it takes to double. So 15 divided by 5 would give you 3. The only time that it'll come out exactly the same as the time is if something's happening every 1 unit. Then dividing by 1 won't change anything. All right, so that's the formula for something doubling. So let's do this. So it says, suppose 100 bacteria are in a petri dish, and they're doubling every 2 hours. When will you have 350,000 bacteria? So you might think, well, that's a lot, right? It's going to take a long time. But if something's doubling, it gets there pretty quick. So for this one, again, try to pick a variable that would make sense, or a name for your function. we're finding an amount of bacteria. So you could use A for amount or B for bacteria. I'm going to use B. The amount of bacteria as a function of time. Okay. What's the first thing that comes after the equal sign?
Initial.
And what's our initial amount here?
100.
100 times. Now this is exponential growth, but it's very specific. In the last problem, I gave you a percentage to fill in. This time I'm not. You need to know what number has to get filled in right here based on that word. What number goes in the parentheses this time?
2.
2. Okay. I will not tell you to fill in a 2. You'll need to know that. Okay, so it's always a 2 for doubling. And then the exponent is t divided by the length of the time to double. How long does it take to double in this problem?
2.
Yeah, just a coincidence, it's a 2. Okay, so there's your formula. And they want to know when we're going to hit 350,000. So I could ask you, once you get your formula, I could ask you two different types of questions. I could say, tell me how much bacteria you'll have 20 hours from now. Or I could say, tell me how many hours to hit 350,000. Okay? So we have to know where to plug that in. Does the 350,000 get plugged in for t or b of t?
B of T.
Right. This would get plugged in right there, and then you do essentially the same thing we did in the last problem. I would set your y max maybe at like 400,000. You're going to end up with something like this. One graph is going to curve up. That's going to be the bacteria growing. And the red line is going to be when they hit 350,000. And then you'd have to calculate the... Yeah. Yeah, you just calculate the intercept. Yep. Okay, so I wasn't going to type that one in because we just did it. Any question on how we did that one? Okay, just don't forget this. That's important. Okay, so that's doubling. What do you think the opposite of something doubling is? It is going to be decreasing, specifically how much? By a half. Okay? And that's the last one we're going to look at, and that's called half-life. So half-life is a specific example of this. Okay? It's a specific example of exponential decay. And what half-life is the amount of time for half of a substance to decay. So what that means is, let's say you have like a nuclear power plant, and maybe you made 100 pounds of nuclear waste. And let's say the half-life of that material is 1,000 years. So after 1,000 years, instead of having 100 pounds of waste, it'll have broken down into 50 pounds. After another 1,000 years, instead of 50 pounds, it'll be at 25 pounds. After another 1,000 years, it'll be at 12.5. So every 1,000 years, half of the radioactive material breaks down and is gone. So if it has to be, say, under a pound to be safe, I'll just make that number up, it's going to take thousands and thousands of years to happen. It's going to take a long time. And that's the formula for half-life. Very similar to doubling. The only difference is instead of 2 in parentheses, it's 1/2. Other than doubling or halving, if it's something besides one of those two, I will always give you the percentage. Like the population of the town growing at 2.5%. The other thing with a percent is you have to figure out if it's 1 plus r or 1 minus r. But you should be able to tell that from reading the word problem. If it says the population is increasing, use growth. Decreasing, use decay. Let's try that one. So it says the half-life of a substance is 20 days, and you are starting with 5 grams. Okay, let's make a formula for that first. So we're figuring out an amount. So I would probably name my function A. The amount of radioactive material as a function of time. What's going to come right after the equal sign in this problem?
5.
5, that's the initial amount. And I did not give you a percentage, but I told you it was a half-life problem, so you need to know what goes in parentheses. 1/2, yep. And what's going to be my exponent? Time divided by 20. Because that exponent has to be the number of half-life cycles. So if 20 days have gone by, plug in 20 for t, and 20 divided by 20 is 1. That's 1 half-life cycle. Okay, so there's our formula. Any question on the formula? Okay, so last thing is find an algebraic representation. We've already done that. So now I want to know when there will be less than 1 gram. So first thing to decide, are we going to plug in 1 for t or a of t?
A of t.
Right, that 1 gram, that is not a time. That's an amount. We're solving for the time because the question is when. So that's when something is going to happen is a time. So let's fill in the 1. Now, if you notice when I wrote that, you might say, well, that doesn't answer the question exactly. The question is, when will there be less than 1 gram, not equal to 1 gram? And I know that. But when I graph it, I'm going to interpret my answer because I can't type an inequality into the calculator. I can only type in equations. So type that in and then interpret our answer from there. Okay, what's going to go on Y1?
5 times 1/2
Sure, we can do 5 times 1/2.
to x divided by 20.
X divided by 20. Okay, and then what's going to go on Y2? 1. Definitely not a good window for this problem. What's the amount of substance that we're starting with? 5, and it's only going to go down from there. Okay. As it goes down, it's going to get lower and lower, but it's never going to reach what? Yeah, it's never going to reach 0. So essentially that means once you have this nuclear waste or whatever it is, it technically never goes away. It gets smaller and smaller and smaller, and eventually it becomes more and more insignificant. But it's always there a little bit. And X is the number of days that have gone by. Let's go out to at least 4 half-life cycles. Just an estimate. How many days is it going to take to get through 4 cycles? It's going to take 80 days. So let's go up to 80. If that's not enough, we'll look a little further. So I just messed up my window somehow. Probably put a min bigger than the max. So 0 to 5. Okay, so there's our substance decaying. Are we going to get less than 1? Yeah, I think so. Okay. So now, using that, what do I have to find?
The intersection.
Find the intersect. Now we just have to interpret that answer. So the question is, when are we going to be less than 1 gram? How many days have to go by to make sure that we are less than 1 gram remaining? Well, we'll round to 2 decimal places there. But we have to be careful how we write our answer.
46.44.
You gotta write a little bit more than that.
46.
No, the number is okay. You can use 46.44 in your answer, but you have to elaborate on your answer a little more.
Days.
46.44 days. We need a little more though.
Anything greater than
Yes.
46.44 days?
So the number of days has to be greater than 46.44. Anything after 46.44 days, and you're going to be on that part of the curve, you're going to be under 1 gram. If you did anything before 46.4 days, you'd be up here. You're above the red line, and that's not what they wanted. Okay, so that's how you have to write your answer, as an inequality. That's what I was getting at. And that's exponential functions. So any questions on that? So all the kind of standard things we do: look at the transformations, couple word problems, and then describing, looking at sketches and finding intersects. Okay. So tomorrow we'll look at the last function in this chapter, which is logs, and that's the one we're going to split up into 2 or 3 days. Because there's a little bit more going on with logs, but that's good for this one. Okay, let me double check that. Okay, so homework on 268, it's 4 through 7, 19, 25, 27, and then 47 and 49, and 57. Okay, so we'll take a look at that tomorrow, and then we'll do section 5.4.